All right, it's time to get going on 310. Basically, what this mostly is a bunch of applications here. So it's going to be, quite a few just examples going through and doing them. But this skill that we're going to try and develop here is actually a very good skill to have. Uh, Very useful in a lot of science fields and a lot of engineering type fields and things like that. So pay very close attention to this, not only for just your future in these kinds of things, but also in in the test that's coming up. So let's take a look at this. So example one, everything changes with times. All right, we're doing related rates here. Suppose that a dimension x and the area A equals 7x squared of a shape are differentiable functions of time t. Write an equation that relates the change in area to the change in the dimension with respect to time. So we have the dimension x and we have an area and how it relates to x, and we're assuming both are differentiable with respect to time. So we need an equation that relates the change in area to the change in dimension with respect to time, the dimension being x. So we need something that relates the change in the area to the change in x, okay? And so the easy thing to do here is simply take the derivative of both sides. And so on the left side, we'd have the derivative of a with respect to time, right? Just implicit derivative. And then here, we need to take the derivative of 7x squared, remembering x is a function of time. And so we bring the 2 out in front, and we get 2 times 7 is 14. We end up with the x, and it becomes to the first power. And then this is times the derivative of that x, which is dx dt. And that's it right there. This is our change in area here related to our dimension changing with time, okay? The only other way you might maybe come across this written would be like if you multiplied both sides by dt and it canceled out the dt, and sometimes you might see it written like this. So just keep in mind those two basically just follow right from each other. But anyway, that's the one really more that I'm looking for here. Okay, so let's look at another example here. Here we're going to assume that x equals x of t, so x is a function of time, and y equals y of t, y is a function of time, and they're differentiable functions of t, okay? If x equals y cubed minus y, and dy dt equals 5, then what is dx dt when y equals 2? All right, well, dx dt is going to equal dx dy, that was an x, times dy dt. Okay, that's just chain rule right there. Well, we know what dx dy is. We can just go ahead and just do it right there. So we'll come over here and we'll say x equals y cubed minus y. And so dx dy is going to be 3y squared times dy dy, which is just 1, minus dy dy, which is just, here, I'll actually write it, dy dy minus derivative of y is dy dy. That's a 1, that's a 1. This is 3y squared minus 1. That's what dx dy is. So we can come over here and write it. That's the dx dy right there. So this is 3y squared minus 1, okay? And then dy dt, well, that's given to us. It's given to us right there. It's 5. So we put a 5 in there, all right? Then we can distribute. This becomes 15y squared minus 5. And then we need to plug in when y equals 2. So this dx dt is basically, it's the derivative of x as a function of time, right? But we don't want to just plug in any time. We want d dt, right, we could say it's like operating on that function of time, is here. This is what I'm saying there. Sorry, just clarify. That's dx dt is the derivative of x as a function of time. So we can make it like this as a function of when y is 2, just like that. And then this will equal plugging in 2. So this is 15 times 2 squared minus 5. 2 squared is 4, and 4 times 15 is 60. So this is 60 minus 5, which just ultimately equals 55. And there's the answer. All right. So, this takes a little bit of practice, a little bit of getting used to, but ultimately, this is what what this section's about, is coming up with these like differential type equations with, taking a derivative and then trying to substitute around until you can get it. All right, so let's look at another one here. If x squared plus y squared equals 25, hopefully you recognize what that is an equation for, and dx dt equals -2, then what is dy dt when x equals 3 and y equals -4? So we need a relation. We're trying to find dy dt, and dy dt, chain rule, will be dy, so something like this, right? You need something like that, times that. So we get that dy dt. And then we need to put the same thing here and the same thing here, right? Chain rule. So we're going to put a dx, because that's the other variable. We have y with x, and that's what we need, x, y's, and t's. So we take a look at this. We know dx dt, that's given to us. It's right here, right? It's a -2, so this becomes a -2. We just need dy dx. So we get that by using this equation right there. So we're going to do d dx of x squared plus y squared equals 25. And we're going to go through and do the derivative. This is going to be a 2x dx dx plus a 2y dy dx. And then over here, the derivative of 25 is just 0. It's a constant. Okay? This is a 1. So we end up with just this, and we can solve for dy dx. We can subtract the 2x over, divide by 2y, and we end up with 2y dy dx equals -2x, divide by 2y dy dx equals -x over y. All right, and there's dy dx, which means we have it, which means we can come back over here and substitute it. This is -x over y times -2. And that gives us 2x over y. And then if we want to plug this in, they're asking us when x equals 3 and y equals 4. Notice this dy dt, this is dy dt, is the derivative of a function, right, of y as a function of x and y. There's both x and y in there, so it's a function of both those things, which means we have to plug them both in. So this is d dt of y, I guess I could put parentheses in, that's the part we're taking the derivative of, y of 3 -4, and so we plug in 3 for x and -4 for y, just like that. And 2 over the 4 is just a 2 in the denominator, so this is -3 over 2. And there's your answer. Okay? Hopefully this is making some kind of sense to you. So let's try another one. Like I said, best thing to do here, just example, 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 example. So here we've got x and y being differentiable functions, right? And we're going to go through and start doing some of this, okay? So let's see here. We've got x and y differentiable functions of t, and and let s equals x squared times the square root of 1 plus 2y be a function of x and y. How is ds dt related to dx dt if y is a constant? All right, so ds dt is going to be, and again, we split it, ds and a dt like that. And then the other thing we have is, we have x. So dx dx. And please remember this part. Y is a constant, okay? We're treating y as a constant, so we can't do a ds dy and dy dt. That's constant. So this becomes something we gotta find these things. So we have dx dt, and we can go through and start doing this. So d dx of s equals x squared times the square root of 1 plus 2y. Okay? And so this is ds dx equals, and here remember, y is a constant, right? We're treating y as a constant. Okay? If it's a constant, then that whole square root is a constant, and we just carry it right along, and this becomes 2x dx dx, which we don't have to write 1 because it's just 1. And so we get this, 2x equals the square root of 1 plus 2y. Therefore, we come back over here, ds dt. Well, we have ds dx now. That's 2x times the square root of 1 plus 2y. And then it's times dx dt. And there you have it. That's ds dt related to dx dt. Okay. Next, I think I'll leave part C for you to try yourself, but let's take a look at part B. How is ds dt related to dx dt and dy dt if neither x or y is a constant? So neither one of them is a constant, then, how are they related? Well, if we write ds dt, we can't just say it's dx over dt dy dt. Those are not equal, right? There's nothing that's going to cancel out. These two things, not equal. So we can't do that. But we can look at this, what is ds dt? Well, we know that dx dt, we can write that as dx dy dy dt, right? Where we kept the dx and the dt there. Okay, and we can look at dx dy then as dt dy dx dt. All right, fix that d a little bit. And this was a times. Okay, so dx dy is dx dt. That's, hopefully you can see what I did there. I basically just took this and I divided both sides by it, which gave me dt dy, gave me the reciprocal of it on the other side. Kind of like if I had said, I have 1/7 times x equal, or let's make it 2/7. 2/7 times x equals y, I can say that x equals 7/2 times y, right? Reciprocal it to the other side, which is essentially me multiplying everything by 7/2, right? Both sides. And that's going to cancel like that. Okay, well, it's the same sort of thing here. It's like I multiply both sides by dt dy, and that cancels on this side, dt dy, like that. Okay, that's kind of like what I just did there to make that work. Okay, and you end up with what dx dy is. Well, if we come back over here, ds dt, we can write that as ds, gotta follow me on this one, ds dx, dx dy, and then dy dt. Okay, see that? ds dx, the dx's, here, do it in blue real quick. Dx, dx, dy, dy, and we're left with ds dt. And all that cancels out. Okay, so we can write it like that. And then we have basically what we've done. We just substituted this dx dy, or this, sorry, this dx dt. We can basically put it over in there. So anyway, as we're going, this is ds dx, and then dx dy. Here's now where I'm going to do the substitution. This equals this, which I'm going to plug right into there. Okay, so this will become dt or we'll put dx dt first. That's this one, so we'll put that there first, times dt dy times dy dt. Okay, and right now we have it related to dx dt, and we don't quite have, and we have a dy dt. We have them both in here, but what we're missing are the other two things to get that out of there. So we need ds dx, and we need a dt dy things to substitute out of there. All right, so we can take the derivative of s equals x squared times the square root of 1 plus 2y, and then ds dt is going to be, now remember, neither one of these are constants. So I'll move this over a little bit. So I have to actually do the power or the product rule here. So this is 2x times the square root. This is 2x, and then dx dt times our square root of 1 plus 2y plus the x squared. And now we have to do the derivative of the square root. So that's bring the 1/2, right? Because square roots are a 1/2 exponent. Bring that 1/2 out, and then make it to the negative 1/2 power, which is a 1 over square root of 1 plus 2y. And then times the derivative of what's on the inside. Well, the derivative of 1 is 0. The derivative of 2y is 2, and then dy dt. Sorry, I know I kind of crunched that in there, but there you go. All right, and that's ds dt. Okay, and so what I want you to do is I want you to try to finish this one here yourself. Try and get this figured out, and really see how you can do on part C, and then that'll finish this question for you. And then come take a look back at the notes to see what the actual answer is. Okay, so let's go ahead and go out of there. Okay, so there's our ultimate relationship. But anyway, try part C, try finishing this problem, finish it up, do part C, and then come back and take a look in the notes to see if you got the right answer. Okay, same thing for the next one. Here, let's take a look at this one. Heating up a plate. I want you to come back and try that one on your own and see how you do. This one, just see how you can do this. And then changing the dimension of a rectangle. You know what? Actually, I'm gonna do this one here on the heating plate, and you try the changing dimensions on a rectangle one, and then come look and see what I did. So I'll do one of them here. All right, so given when a circular plate of metal is heated in an oven, its radius increases at a rate of 0.01 centimeters per minute. At what rate is its area increasing when the plate's radius is 44 centimeters? So if you think about this, if we have a small circle and we take a tiny little step dr, a tiny little change in its radius, we're going to get this amount of new area in it, right? But If we're out here later on, when our circle is bigger, and we do that same tiny little skinny dr step, we're going to get a new amount of area that is equal to all of this area. And so depending on how large your circle is, when you do that same tiny little step in R, that tiny little dr change, right? You're doing this tiny little dr step, same little dr step over here, it gives you a different amount of area that has been added onto it. So depending on what the current radius is, your next step will actually change the rate at which the area is changing. The rate at which the radius is changing is staying the same, but the rate at which the area is increasing or decreasing or whatever, whether or not you're making the radius bigger or smaller, is going to change depending on what your current radius is. So let's try this. We are given dr dt equals 0.01 centimeters per minute, right? And we're asked to find dA dt. What is that? Okay? And we're asked to find that specifically when the radius equals 44 centimeters. So that's what's given. All right, so what do we know? What do we know about circles? Well, the thing I know about circles, thanks to Archimedes, is that area equals pi r squared. Okay, and so now what I want to try to do is find a relationship between the rate at which the area is changing and the rate at which the radius is changing. And the area and the radius are both in this equation. So I can simply take the derivative of both sides with respect to time, dA dt, equals pi is a constant, so we just carry it along, and do the derivative of r with respect to t, 2r times dr dt, okay? And right now, there you go. I have a relationship between the the rate of change of the area and the rate of change of the radius, okay? And so I just need to plug these in. So this is, we want the rate of change of the area at, what was it, 44 centimeters. And so that'll equal pi times 2 times 44 centimeters, we're just plugging everything in now, times dr dt, which we were given, is 0.01 centimeters per minute. Okay, now remember, an area is a length squared. It would be like a meter squared or a centimeter squared or whatever. And you notice we'll have a centimeter here and a centimeter here. So we'll have a centimeter squared in the numerator. And so we'll have a centimeter squared per minute, which is what we'd want here. We want an area per time. So a centimeter squared per minute will fit. So this seems to work very nicely dimensionally. And we just start multiplying this all together. So this gives us 2 times 44 centimeters times 0.01. So 2 times 44 is 88 times 0.01 is 0.88, and then pi centimeters squared per minute. Okay? And if you wanted to plug in pi, you'd get about 2.76 centimeters squared per minute. Okay? And so I don't know which way, but either one of those is probably a pretty decent answer. Okay? I want you to try working on example 5. See how you do with it. Okay? See how you do with example 5. Try and figure this one out. Now, again, this one, it's going to involve figuring out what the area of this box is. Okay? So think about an equation that would tell you, well, not the area, but the surface area of the box. Okay, so think about how you could write out what the surface area was. It'll be something equal to 3 terms, and then start taking the derivatives, okay? So that one's a bit of a challenge one, but give it a try, and, go from there and see how you do. Okay, so let's take a look here at the next page, and then it's going to basically just go over some problem solving strategies. You should look through this. I highly recommend, if you can, if it's one where there's a picture, draw yourself a picture. I did that back here where I just kind of drew a picture of the idea to get an idea of what was actually happening. On this one, you're going to want to draw yourself a picture, right? You're going to want to draw yourself a picture of this, of this box. And then maybe do it a little better than I did it. But draw yourself a picture of this box, start labeling things in it, and, gives you some sort of physical idea of what's going on. So draw a picture, write down all the information that you're given, and the symbols. Okay, the symbols, maybe some that you have to choose, maybe some that are given. Write down what you're asked to find. I did that before too. I wrote down what was given and what I was trying to find, right? I did that right here, given, here's the information given, here's what I'm trying to find, there's information I'm given, just to help keep track of it. Write an equation that relates the variables. So just write, that's this right here. This equation relates those variables together. Then differentiate with respect to time. That's this right here. And then evaluate. That's this part right here where we plug numbers in. Okay, so just follow that kind of basic formula, go through and try and solve them and take a look at this. There are more to be done, but I'm going to do that in a different video because this one's getting kind of long. All right, thanks.